Okay, so it is my pleasure to introduce our first keynote speaker of the meeting, Dr. Jim DiCarlo. So Dr. DiCarlo is an investigator at the MIT McGovern Institute and is also the Peter de Flores Professor of Neuroscience in the Department of Brain and Cognitive Sciences at MIT. He recently also became the director of the MIT Quest for Intelligence, which is an interdisciplinary institute aimed at advancing research in natural and artificial intelligence. His overall research goal is to discover and artificially emulate the brain mechanisms that underlie human visual intelligence. So Dr. DiCarlo has a very broad training that encompasses engineering, medicine, systems neurophysiology, and computation, and includes a bachelor's degree in biomedical engineering from Northwestern, MD and PhD degrees from Johns Hopkins, as well as advanced training with Ken Johnson at Johns Hopkins and John Mounsell at Baylor. And over the past 20 years, he's applied this very broad interdisciplinary range of skills to helping develop our understanding of the neural mechanisms that underlie visual information processing in the ventral stream, including, in particular, core object recognition. His group's most recent work involves building and testing new computational models that currently provide some of the leading scientific hypotheses about the neural mechanisms operating along the ventral stream. And importantly, his group has also demonstrated how these models can be used to non-invasively control neural activity patterns deep in the brain. And they're also working to causally test those models using neural perturbations to explore how particular neural mechanisms might develop from supervised and unsupervised visual experience. So ultimately, the goal of this work is to seek an end-to-end understanding of the neural mechanisms of human visual processing that can be used not only to gain insights into how sensory representations are altered in conditions such as agnosia, autism, and dyslexia, but also to guide the development of new artificial vision systems. And this includes new neural prosthetics to restore or augment lost senses. So in recognition of this very impressive body of work, he has received a number of highly prestigious awards, including, among others, the Alfred P. Sloan Research Fellowship, the Pew Scholar Award in Biomedical Sciences, the McKnight Scholar Award in Neuroscience, and the Peter de Flores Professorship at MIT. So it is truly a great pleasure to welcome him here today. His talk is entitled Reverse Engineering the Neural Mechanisms of Visual Intelligence. So over to you.
Okay, great. Could you give me a thumbs up? You're hearing me just fine?
Yes, we can hear you just fine.
Great. Okay, thank you so much for that kind introduction, and thank you for inviting me. I have titled the talk Reverse Engineering Human Visual Intelligence, but I think the proper title could have been something more like this: Computable Hypothesis Building and Testing of Integrated Sets of Neural Mechanisms that might underlie part of visual intelligence. But the first title sounds more fun, so we'll stick with that. I want to say at the outset here that everything that I'm going to show you from my lab is really done by these amazing women and men. And I'll try to highlight some of them along the way. I'm really just an ambassador of all of their great work. So the question that motivates us, as it was said at the introduction, is really how visual intelligence works. Here's just an example of that from a static scene like this one. Just looking at an image like this one, you're able to answer questions like what's in the scene, where are the cars, where are the people. Harder questions like what will happen next, which relates to things like where is it safe to walk, and then of course visual intelligence bleeds into general cognition. And we have not answered all of these questions. The field doesn't know all the answers to these questions. Our lab has worked primarily on the ones on the left, so just what's out there, what are these objects? And I'll show you a bit of a tour of that, but also give you kind of a sense of I think a philosophy going forward that might connect to lots of the other talks and the panel discussion that we'll have about how we as a science should be approaching questions, not just these ones, but broader questions like some of the ones I've put also up on this slide. So to the specifics of what we worked on in our lab, we focused on the ventral visual stream as mentioned, which is really processing the central part of your visual field, where if you fixated this red dot here, you would be, that's meant to illustrate your high acuity center of 10 degrees of visual field that we are going to focus on here. And what you do, you sample a scene like this one, is you don't just keep your eyes fixed at that red dot, but subconsciously you're making lots of eye movements around this scene, fixating various points for just a couple hundred milliseconds each, rapid eye movements called saccades between those points. And you see during those brief glimpses of just a couple hundred milliseconds. And it's been long known that you can take in a lot of information in just those couple hundred milliseconds. And that's what we've focused on here. We've operationalized the problem of just 200 milliseconds of viewing duration or so, and central 10 degrees again. And I've illustrated that here with these little snapshots but you can imagine these appearing in sequence. We refer to your ability of being able to extract one or more objects and its other latent content, like its pose and position, within those 10-degree windows. We refer to that operationally as core object recognition. So for instance, is a car here? Is a person here? What is the pose of the car? And so forth. So that's we think of as a foundational component of vision. It's not all of visual intelligence, but it's sort of an entry point to those larger questions of visual intelligence. And that's largely what I'll focus on today, is telling you about the history of that work and maybe how it connects to ongoing future work. So to give you a sense of operationalizing that in the lab, so that one way you might do that is I'll just sort of give you glimpses here, just 100 milliseconds, and let you try a few trials. So if you fixate that dot, I'll show you an image. I didn't tell you what category that might have come up with, but when you're faced with these two choices, I'm sure most of you, even without any pre-queuing, could say, well, that's more likely an image of a bird on the right than, say, an elephant on the left. And here comes another one coming at you now. Okay, again, it was a bird. That was more of a natural photograph. Okay, we can test you all day long in that way. We can also test this organism, our favorite animal model system. This is the rhesus monkey, doing the task that you just did, triggering a new test image at the center of the screen with a touchpad, and then choosing among two choices here. Animals are quite good at this. It takes them about a day or two to learn any new object. This animal knows dozens of objects. They do this quite naturally, many thousands of trials. And by collecting lots of data from this species and from humans, we're able, I'm not going to show you this here, but we've shown that humans and monkeys are almost identical, quantitatively equivalent in our abilities to do the task I just showed you, core recognition. So that's illustrated here on the right side of the slide by this approximate equivalence between these two forms of primates. Of course, the human primate is the one we're most interested in. What I'm also showing you on the left is these, I'll call them wannabe primates, which are computer vision systems, which I used to say were much worse than primates. Now I say they're approximately, but not quite equal to. They've been improved by some of the methods and new models that you'll see throughout the rest of my talk, but those systems are still not quite up to the task of matching us, but you have to work much harder to see the differences now between computer vision systems in these tasks and what we and our primate cousins do in this task. Again, this is all around core visual recognition, just summarized here schematically. So the reason we work on this monkey system rather than the human is because we have much greater access to the neural circuitry that could underlie this processing. And this is a series of areas called the ventral visual stream that have long been known, this network of areas, to be implicated in the task of core recognition and central visual processing more broadly. So again, this network of neural mechanisms, it's been evidenced to be critical to core recognition. It lives in these set of areas here, which has millions of neurons in each of these cortical areas. It's illustrated schematically here on the bottom. And we and others have been long interested in what are the processing mechanisms that are going on there in that ventral stream. To orient you, these areas here is a series of cortical areas. V1 is the lowest area, V2, V4, and infratemporal cortex, which is a constellation of areas, projects to regions in the other parts of the brain involved in decision and action selection. So we think of this as sort of the visual network that then has to feed other cognitive and action networks. And as a bit of background to orient you, and when we and others record neurons in IT cortex, here now illustrated with this red box, and now when we record from these areas, here we record often with chronically implanted recording arrays, such as these shown here. These can be implanted during a sterile surgery, and then the animal can be reconnected to connect to a port on the animals every day to record for hundreds record thousands of images at many repetitions over many months of recording. And this is, again, electrodes implanted in brain tissue recording from single or multi-unit spiking activity. In this case, in IT cortex, we and others can record from other parts of the system as well. When you record from IT cortex, here's an example of a few hundred neural recording sites shown here as a vertical column here, which the intensity of the color indicating the neural spike rate coming out in about 100 millisecond time window. I don't want to kind of go into all the details of these recordings here, but just to give you the high level picture here is that you can think of each neuron or neural site as yielding a different amount of spikes, a different spike rate in response to each image. Here's one example image shown at the top. And here's the sort of population pattern, if you will, that's yielded from this image shown here in actual data in the columns shown in green to black. That is kind of an example of a sampled image pattern analogous to the simulated image patterns I'm showing you in red on the left. Okay, you can think of these, if you're a computer vision scientist, as a feature vector, and we can sample those not just from one image, but as I mentioned, recording for many months can sample from many images. Here's 8 images. Notice that these patterns are different for each image, which shouldn't be surprising to you. They're also, I didn't say this, but they're reproducible. When you return to the same image, you get essentially the same pattern out again, modulo Poisson variability, known Poisson variability of cortical neurons. Okay, again, that's 8 images. Here's thousands of recorded images. This gives you a sense of the kind of data volumes that we and others can collect in this species. And so one of the things that I want to give you in way of background of these data is that it's been long known that we and others have shown that if you build linear decoders on these population feature vectors up in IT cortex, that they readily produce patterns of behavior on new images, that is generalizing to new images, that match the abilities of both humans and, as I said earlier, monkeys, because they're equivalent, match those abilities in their generalization ability to do tasks like core recognition. In other words, if you had an IT population representation computed from the image, you would be a linear decode step away from being as good as the primates and doing these kinds of behavior. That is not a fully closed understanding of the linkage between IT neurons and the behavioral patterns themselves, and there's many questions up there. But for the purposes of this talk, I'd like you to just keep in mind that you can think of this as the IT code to say it's already quite powerful in doing tasks like core visual recognition. So this gives us some cognitively relevant grounding in the brain. Again, these population patterns at the neural spike level are a sort of magic in a way, that they do these kind of tasks that were quite mysterious for some time. And the rest of my talk is really about trying to understand how those are computed from the photons striking the eyes, the pixels here on the left. Okay, so this is what I just set up. If you accept all that background, which again is over many years or decades, there's an IT code that's computed at the top of the ventral stream by the brain. The questions now, one of the holy grail questions is, how is this IT code computed from the image? Another way of putting that is, what is the integrated set of neural mechanisms that intervene between the pixels on the eye, or the photon striking the eye, which you can think of as a pixel array, and all the patterns of neural activity that are produced up to IT cortex? And I don't mean only in a feed-forward path, but both the full recurrent network is what we'd like to understand to give rise to those patterns that we record in IT cortex. That's long been the holy grail question for us and for much of the field. As a bit of an aside to kind of orient you to other talks that you might be hearing, this is a how question of how things are being done. We'd like to know the actual mechanisms that are implementing this. This is a question of adult online function. So this is not a question of how the neurons are developing or maintained. Those are equally important questions. They're just not the ones that we're referring to here. And again, it's not the only interesting question you can ask about vision, but all of that is by way of context for what we're after here, is an understanding of the integrated set of neural mechanisms that are operating online in the adult system to produce the behaviors that we can observe, quantify, and compare. Okay, so this is a complex, long-standing systems level science question. And this really where it gets to a little bit philosophical here. How, as a field, are we going to proceed in even understanding a system like this one? What does that even mean? And I need to take a bit of a detour here to give you kind of our philosophy on a systems level science approach to this. And the idea, the basic idea goes like this. You have kind of neural mechanisms that you'd like to understand at a scientific level. They're a large set of integrated mechanisms. So what you do to approach this in our mind is you start by building something, which I'll refer to any building as an engineering related activity. So building some starting ANN models. ANNs are artificial neural networks. If you're interested in neural mechanisms, then anything you're building as a model, it better have some neurons in it. So the proposed hypotheses that you're building, they must have neurons if you're a neuroscientist and you understand neural mechanisms. So that's why I'm using the term ANN here. ANN, artificial neural network, because it has mappable units that are meant to be actual neurons or approximations of neurons that are explaining the complex behavior that you're trying to explain. Then you build those neural networks and you then evaluate them. And I'll say more about how we evaluate them, but you're going to evaluate them on matching the things that you're empirically observing, which usually are going to mean brain measurements like neural data like I just showed you, or also behavioral tests as well. And so you're going to evaluate those networks, and then you're going to come back and say, well, whenever those things match up well, I'll say that's a good model, but they're never going to match up perfectly. And any discrepancies you see between the match, you're going to use to then try to update and build a hopeful better model that better matches what you're seeing empirically. So you do some more engineering, you come back, you reevaluate the new generation of models, and then you come back and you build another generation of models. And so it's this iteration between building and testing that is the core of getting to a systems level understanding of a problem like this one. And so I will claim that the best models that come out of this process, the best models are the best scientific hypothesis. And I mean computable ANN models here as scientific hypotheses. And when I say best, I don't mean best in a computer vision contest. I mean they best match the evaluable evaluations in comparison to the brain. And when I say the models are the hypothesis, the data are not hypotheses, the images are not hypotheses, the evaluation methods are not hypotheses, the model optimization methods are also not hypotheses in our language. It's the models of the neural mechanisms that are the things that we're after here. That's the context in which we've been working. And I'll add one last comment to say the science here of doing this is never finished. There's always going to be a better, more accurate model. So we also need to keep that in mind. All of this kind of translates to me into a kind of statement, which is the current best ANN models of X, where X could be any domain of function, here it's core recognition, are the current best neuroscientific hypothesis of the mechanisms of X. Now, I think that statement is kind of logically unassailable, although it seems to be under attack in our field in some ways, and I would love to return to this when we get to panel discussion. But their details matter. So this statement as written is unassailable, but the details matter a lot. So for instance, the word ANN in here, I don't mean today's ANNs are the best models of X. I mean some neural network model, some artificial neural network model will be an answer of the kind we seek as neuroscientists, that the form of the answer will include neural networks of some type, and that artificial in the sense that they're computable neural networks and not just a biological copy or another animal as the model itself. Then a second thing I want to highlight is the word best. So again, I've already said this, but best means best matches all the currently available brain and behavioral data. Again, there will be more data, there will be more to produce, there will be better models, and that's why the word current is applied here. But that is the best. So this is the framework in which we're working, is trying to execute on this hypothesis or this philosophy here. And it's not just a kind of a philosophy of systems neuroscience. Some subfields, including us and others, have really started to put this into practice. And I'll give you sort of a high-level overview of what we've been doing in that regime, and maybe therefore paint a picture of how we may, as a field, take it forward further, but with that philosophical context. Okay, so after that detour and kind of a philosophy of how to do systems-level integrated science, I'm now going to return to our question, visual recognition in the central 10 degrees, first couple 100 milliseconds. This is, again, is a complex, long-standing problem. So I'm now going to take that philosophy and give you sort of a tour of how it's been executing over decades. So the ability, the beginnings of doing this really comes back to like the 1980s to 2010s or so, was sort of decades of work building scientifically inspired models out of engineering those models in a series of models like Fukushima in 1980, a series of other follow-on models, most notably from my colleague Tommy Kojo, HMAX family of models, the Ventral stream. We and others have built a bunch of models that we tried to do during those decades as well. I'm not going to take you through the details of those models other than to say there were model attempts inspired by science for many decades, neural network models trying to model the ventral stream. What I'm going to add here is that when we looked at those models, one of the things that we first wanted to do is ask if this model is actually a good model, a useful model, it better accurately align with the neural data. That's what I said earlier. To be a good model, it should match the data in some sense. And the data I showed you that we collected that were already interesting to us were these IT neural response data that I showed you a minute ago in those green colors. Here's an example of an IT recording site recorded over many, this is many images. This is not time on the x-axis. These are just many images. This is the mean spike rate. And you see this neuron wiggles up and down. It changes its mean firing rate depending on what image is shown. And that's, of course, well known. And I said at the beginning, I also said that populations of these neurons give you a quite powerful linear decode to object recognition, like being able to say there's a chair there or not. Now, but do the models predict this data accurately or not was the question we wanted to ask. And not only IT, but say an intermediate level area. Here's a recording of a neuron in area V4 with a similar set of images. And you see a complex response pattern coming out of this neuron. Okay, so to evaluate that, what we do is we take any neural network model, its set of features, and we ask how well do they predict, explain and predict those kinds of neural response data. And so the way we do this, and this was already alluded to in Jean Remy's talk, and it's quite important here to understand, is what we do is we take a feature set out of some level of the model. Here's some level of HMAX. We take a learned weighted sum of those features, of their outputs in response to images, and we ask them to predict the response of each individual neuron. And so we can learn a new weighted sum for each neuron, and it's really quite trying to ask is like, are these neural recordings in the spanning basis of the feature set of these models here? That's essentially what the approach is asking. And then we check the match of the goodness of this match by predicting the neural response on trying to predict the neural response on held out new images. And that's what you're seeing here plotted on the y-axis is a summary of that. This is a median over many recorded neurons, not just one neuron, but a median over recorded neurons. And this is just for one feature set out of one model. And this is shown as a bar here for this example that I'm showing you from an HMAX model. Okay, that's a bit of a technical detail, but I just wanted to give you that census. Explained means predicted for new images. That's what explained means. And this is already corrected for experimental noise limits. So you shouldn't worry that we're not up to the ceiling here because we have noisy data. That's already accounted for when we take these kinds of measurements. And what we found, back to the model production pipeline here, is we found that these early first generation models, they were very poor at predicting the brain responses. This is cortical area V4. Guessing at the V4 response would be at 0% down here, and perfect would be at 100%. And so you can see they're closer to guessing than they are to perfect at 100%. And you can see that visually here. Here's the model's prediction in red, and here's the neural data in black that I showed you a minute ago. This is not just true of V4, as you might expect to go even higher, deeper in the system. This is IT cortex, also quite poor as well. Okay, closer to guessing than to perfect. All right, that was a couple decades of work. It said we have some inspired models, but they just weren't up to the task of matching what we were seeing internally in the brain, at least not very well yet. Then the second generation of ANN models came around. Now that generation of models looks a lot like the first generation. These are deep convolutional neural networks, exactly like the first generation of models. Those, again, were constrained by scientific constraints in neuroanatomy and others that inspired that class of models. And that were engineered into those models to begin with. So this is really just a redraw of the first generation of models here. What was different in the second generation of models is that people started to take seriously the top-down constraints, the ethological goals of these models, not just trying to build them bottom up the way that a neuroscientist might, but to say a cognitive science approach to say, you got to have success on some tasks here. These neural networks are here for a reason in the brain, is to succeed in some abilities. So what we did in our group and others is to start to say, well, we think areas like the ventral stream that we're interested in, they're doing tasks like core recognition. That's what I said at the outset. So let's train these models to do well on these tasks. So we keep the basic architecture. We optimize the unknown parameters of these models to try to do well on tasks like core recognition that I introduced at the beginning. The ability to say there's a car invariant of slight changes in position, pose, and so forth, or there's a person, and so forth. And when I say we, in my group, this work was led primarily by Dan Yeamans, who's now a professor at Stanford, and a graduate student, Ha Hung, at the time. And what we did was just to think of the engineering as enforcing these top-down goals and doing optimization of the hyperparameters and smaller synaptic parameters that give rise to doing well on this task. The parameters at neuroscience were not really able to tell us exactly. Just view the engineering as a way to get to some set of parameters that does well on the task. And I want to, as an aside here, and it connects to some of the other talks you just heard, this is not one task. You might think this is core recognition. It's critical to know there are many tasks here. There are many objects. In ImageNet, for instance, there's 1,000 categories. You can think of this as 1,000-way training on multiple tasks, and that's important to getting the kind of results that I'm going to show you next. Okay, so what the second generation of ANN model building, again, checking these new models by their linear alignment with the brain systems, in this case, ventral stream, visual area V4, and IT. In black was what I showed you a minute ago when things were not doing as well. And what we were excited about at the time is that we started to see models that were much better, almost twice as good as the previous models in matching what we're seeing in both V4 and visual area IT. So much better, not perfect, I'll say, but much better with just this early generation approach. This is around 2013 to 14 or so for the models that you're seeing here on this slide. Okay, that was quite exciting, and it sort of pointed to a general idea that I think is a theme that you see now in many talks, is that as you improve on accuracy on a kind of a high-level goal task, that you're really sort of guessing at what the reasons it might be that the brain has these neural networks, and you optimize the unknown parameters, and here we think of optimizing performance on core recognition tasks, that led to models that now match the neural alignment here, which is the y-axis on this plot, a better alignment with IT in this case. So we're just extending this correlation here, and you saw that in John Remy's talk and other talks as well. So this is really a virtuous cycle. You can say, let's keep this loop going. And that's essentially what a lot of the field has been doing more recently now, is taking that mixture of top-down and bottom-up approaches. So back to the specifics of what we've been doing is we first asked, are these aligned at IT? Are these aligned in V4? And I showed you some of those results that show that are pretty aligned in IT in V4. And again, sort of impressive alignment that was really quite exciting at the time. Not perfect, but it was impressive, and it sort of drew our attention to keep working in this approach. We also later checked the behavioral alignment, and we saw, again, much better alignment at the behavioral level, but still not perfect, as I alluded to. And we and others have been asking at lower levels as well, in V2 and V1, how well these are aligned. And I'll say a little bit more about that later. So now this is the game now. How do we find even better and better alignments between neural network models and actual brain measurements at a subsystem like this one, or other brain systems that you heard about in other talks? So the big picture that I think I'd like to present to all of you here, as you think about kind of this intersection between brain science, neuroscience, and cognitive science, mostly on the left, and engineering on the right, or AI, is that really what's going on is you have this sort of anatomy and task goals driven from the scientific goals, and you have kind of performance optimization tools coming from engineering and other subfields. And those come together around what I call deep in silico neural networks as intelligence algorithms, in our case for visual inference tasks. And for neuroscience, these return as hypotheses that can be checked, again, in the way I've been describing. Do they match? Where do they not match? And then that, of course, returns that loop to try to update that as well. So it's this merger, this union that's sort of leading to great gains in neuroscience, and as I'll show you, also for gains in engineering as well. And again, as I've already mentioned, this is not just vision that we have been doing this in the ventral stream. Others have been doing this in the ventral stream and other parts of the visual system. Others in audition, somatosensation, decision making, motor planning, control, navigation. You heard about language as well. So there's a lot of work in this area, and I'm sorry if your name is not listed here. It's just some of the names that I know that are active in some of these spaces, and it's really just a partial list. So back to kind of where we're in our field here, what we've been trying to do over the last 5 years, we and others have been evaluating really dozens of neural network models, ANN models, on using primarily those linear regression methods that I referred to earlier, and image by image confusion patterns to ask, where are we in this sort of space of how well things line up with the empirical data? And this slide was also shown earlier. I love that. I think Jean-Remy showed the glass half full, half empty. And I think this is an important kind of context to have here, is that models, what we see is that some ANNs, they're demonstrably the leading models of coding in the primate ventral stream in terms of predicting accurately the neural responses and the behavior at multiple levels of the system simultaneously. So they're our best models of those mechanisms that I alluded to as the goal. But they're also, we can see, and I'll be the first to say, these are not the final models. Again, the science is never done. No model we can already see is not perfect in matching the brain and behavioral alignment test. And I'm not showing you all that. I'll give you a little bit of that at the end. But so we have this half full, half empty state. And now the goal is really to try to fill up that glass. We don't dump out the glass and start over. We just say, let's work harder to fill it up more. That's our philosophy. So where are we as kind of a whole right here? And let me sort of step back and sort of say, because this kind of approach is not fully accepted as the way that our field should go forward. And I think, again, this will come up in the panel discussion. First of all, I'll be the first to say this is not a theoretical approach. We have models, they're artificial models that are meant to be emulation models of what's happening in the nervous system. Those in the past have turned out to be very useful as stepping stones towards theories. And I think you're also starting to see that play out now, where even though we don't have full theories of when these models work and when they fail and so forth, that's an active area of work that's now enabled by these models. So the models are really a bridge to theories, even if we don't yet have those theories. I want to sort of come back to the sort of neuroscience version. Often these models are criticized as they don't really count as an understanding. Now, sometimes people mean that in a theoretical sense, but I think they often mean another in a sort of a conceptual sense or other senses as well. And really, they sometimes say, really, is this just a simulation? And it shouldn't count as an understanding. And I'm not actually sometimes sure what to do with that, but instead, as an engineer, the engineering half of me just says, let's just go ahead and go forward with these models. If they're useful, let's not have an ivory tower debate. Let's ask what we can actually do with them. So a good model should be useful in some way. So what can we do with these kind of models? Well, again, if you now take this idea of this interaction between science and engineering, gives you models, there's actually lots we can think of doing with these things. And we've started to try to do the beginnings of some of those things. And I'll loosely refer to these as applications. They're not full applications deployed on your iPhone yet, in that example, but they're kind of use-inspired goals that come from the ability to have a model in your hand today that you didn't have yesterday. And so the kind of things that we most think about are things like neural control, I'll tell you in a minute, brain-machine interfaces. Those are both related to applications in human health. Computer vision applications, of course, are related to this, and also possible things are related to education, visual learning. We've done a little work on all of these, and I'm just going to give you some vignettes on a few of them to give you a sense of what I mean. So neural control. So this was one of the first things we did, and this, when I say we, I mean Puya Bashaman, a postdoc who's now at McGill, and Kohidej Kar, who's actually going to take a position at York. These folks as postdocs teamed up to do this work. And what we did here was the overarching science goal is to direct causal experimental tests of these best models. And I'll show you what I mean by causal and tests in a minute here, but we call this neural population control. And the basic idea is schematically shown here. If you have a neural network model, an artificial model of what you think is happening in the biological neural network shown here in the bottom, then you can do things like take your simulated neurons that are in this neural network, say your alignment with V4, which is a mapping to individual V4 neurons shown here in blue, and you can trace back through the model to the pixels on the image, and you can then use this to say, if I have a control goal, like set the neural activity state in V4 in a particular way, then I can set that control. I can use the model now that I have in hand to design custom images, sort of certain configurations of energy, pixel patterns that are going to be shown to the eyes to try to set the V4 neural activity state into a desired state. So this is a causal test. You're going to put photons on the eye. You're going to cause the neural activity to move in a particular direction. And if the model's good, that causal test will be successful. And here's the model attempting to try to do that causal test now to generate the stimuli for that causal test. Here it's trying to say, this is my preferred image for the goal we set out for the model, is drive this particular V4 neuron up to a high activity state. And here's a model-directed image synthesis, taking a random pixel start to optimize, given the model itself and its parameters, to find the best image to drive that particular V4 neuron. As just one example image of just the process, you can visualize it. Then we experimentally go back and make that causal test by placing that image in front of the animal's eyes and measuring the V4 response in this monkey, where we map the model to those neurons. And here, just by way of giving you a sense of this, here's the model predicted firing rate on the x-axis. Here's the measured neural firing rate from this particular V4 neuron, again, mid-level visual area. Each dot is an image, and you see this very high correlation between the predicted and the actual. That shouldn't be surprising to you, because this is really the earlier work that I described earlier. These models were getting quite good at now aligning with the brain, and that's the work background I showed you earlier. But here we asked the model to go further, to say, find me an image that goes beyond even the outside natural range of that we observed in the biology over a set of natural images. And here's the model trying to sort of now come up with super activating images, or stretch images as we called them at the time. And here's the images it came up with for this particular V4 neuron, shown to its receptive field that's shown here in red. And what we found when we presented these images to the monkey is that this is the model predicted the neural fire rate would be way up here, and the neural fire rate was higher than anything we'd seen before out of this neuron before. So I would call that success. It was able to drive the neuron out of its natural biological range, which is really a success of the model. But the dots are not on the dashed line, which is where they should be if the model's perfect. So again, glass half full, but glass still half empty, but already power that we're getting out of these models that we didn't have before the models. So even only partially accurate computable ANN models allow us to use the control knobs of the world, in this case, the control knobs of pixel energy, to precisely modulate internal brain states. Here I'm showing you for one neuron, but we also showed you can do this for full populations of neurons that we're recording. Again, not perfectly, but far better than we could without this kind of model in hand. Okay, I call that as an example of a neural application that might lead to human health applications at some point. I would love to, if I had time, tell you about our work related to brain-machine interfaces, really beginnings of that work. In the interest of time, I dropped that part of the talk. I'm going to just turn to now a quick detour on the computer vision application to give you a sense of what we did there recently. So now coming back to these general idea, we have ANN models that are approximations of the biology shown here in the bottom. If we go to the behavioral level, which is of course the level most interesting to computer vision, they'd like to have computer vision systems that are just as good, or ideally someday better, than the primate visual systems. So as I mentioned at the outset, some of these newer ventral stream-like ANN systems, now ANN models are of course dominating computer vision, and they were not when this work started, but now they've taken over. They're now competitive with primate behavior on computer vision benchmarks, as I alluded to. But we can see they're still not as robust as visual behavior. You have to look harder, but you can see it. Let me now tell you a little bit of a story where we've been working on just trying to align the models even better. So we take a base model and we're going to update it a little bit to make it a better alignment with the brain. In this case, earlier area, visual area V1. And I'll show you a little bit of computer vision gain that we get out of just making that early visual alignment. And when I say we, this is work led by postdoc Diego Marx and graduate student Joe DiPello. And here's what they did here. So we and others are motivated by this computer vision failure of robustness that we don't think exists in biology, at least not to quite the strong a degree that exists in computer vision systems. And this is this so-called adversarial attack problem. Sort of the flip side of the control I was just describing for you is that if you have a full white box view of a model that, as you know all its details, you can design custom image perturbations like this patterns of pixels shown here, this perturbation here that get added to an image, this image of this terrier shown here, where the ANN would normally say, oh, that's obviously a terrier. You add this pixels to it. And now to you and I, this looks like the same image on the right, but the ANN flips its output to now say, now that's an image of a church. The image pattern, the perturbation is a particularly designed attack to cause this failure of the model, so-called white box attack. One of the things that this is, of course, something that computer vision really doesn't want to have happen. It's viewed as catastrophic. It's viewed as really bad. Somehow it should ideally be fixed. And so what we've been doing, one of the things that DiCarlo and Joel noticed is that if you started to look at the alignments of the neural network models with the brain, again, checking those alignments, here's now the alignment with visual area V1. So that early visual level of a model, you take a model's proposed V1, sort of its early parts, and you ask, how will those features align with the biology V1? And we have measures of that. And those are summarized here in this measure of V1 neural predictivity on the x-axis. And on the y-axis, you just measure that model's robustness to this kind of attack. How some models are better at others than sort of being insensitive or less sensitive to these kind of adversarial attacks. Each dot is a model here shown on this plot. And what you can see here is that there's this correlation. It seemed like models that were better aligned to V1 were more robust to these kind of white box attacks that are shown on the left. And that was a motivating result to us that said, look, if we have a better V1 that's more like the biology, we get a little bit of robustness gain. So let's execute on that bet. And that's not just observe that bet, which is already interesting to observe, but let's execute on it. And what they did was to actually just place a more brain-like V1 from neuroscience at the front of some of these ANN models. I should say as an aside, these models, when trained, they already have pretty decent looking V1s, but they weren't quite as good as the neuroscientific models of V1. And so we were able to leverage those previous neuroscientific models that had been built up over decades. So rather than just emerging from trained neural networks, we now sort of placed a kind of fixed V1 module in front of these neural networks, this so-called V1 module, which has simple cells and complex cells and their appropriate nonlinearities and a bit of stochasticity in it. We then place a regular neural network backbone behind it, and we can place different backbones behind it, different architectures, but they're all deep convolutional neural networks here. Train that whole thing up in the usual way that I described earlier, say on ImageNet training, and then we can ask about its robustness to attacks. And a lot of work to do this fairly, but you can see if you take any backbone, here's a ResNet 50, here's CoreNet-S or AlexNet, these are different architectural backbones. When you put the V1 module in front of it and then train it up and then ask about its robustness, you get robustness gains in all of these different backbone architectures with this V1 module in front of it under both weak and strong attacks. I should say these models are still not as robust as we think human and primate vision are, but you already get these interesting gains just by kind of tweaking the V1 to be more brain-like. We also found it was more tolerating of common image corruption, so-called noise, blur, weather, and digital effects. And we quantified this in this paper, is now a year and a half old or so. And so that was an example of kind of turning the loop of saying, well, let's get it slightly better. And now we're taking that forward to match. If we can get it even matched even better at other levels of the system, we might see even more gains in robustness. And of course, that's this ongoing iteration between building and evaluating and building and evaluating. Okay, in the kind of, let's see, I have about 20 minutes by my count here that I have left. I'd like to tell you two more quick stories. One, I'll spend a bit of time here on this kind of interactive loop, on a sort of story that we've been working on over a number of years that may be of interest to many of you here. So to give you some newer, some things. So this is work by Kohidej Kar, who's a postdoc in the group. And one of the things that Ko was really interested in is let's find where these models are especially vulnerable, where they're especially weak. And here I'm referring to, again, these ANN 2.0 models that I've been illustrating throughout the last few slides. Let's find out where they're weak, where they struggle with. And here's what code did was to test these kind of models on a whole bunch of images and their ability to categorize them correctly. Each dot here is an image. This is model performance on the x-axis and monkey performance, which is equivalent to human performance on the y-axis here. These are in units of D prime, so good performance is high here. And what you notice with these first generation ANN models is that there were a lot of images where you could say, you know, when we're good as humans, then the models are also good. And when we're bad, the models are also bad. So that's good alignment here. But there were a bunch of images up here where the models were somehow much worse than us. These so-called, we call them challenge images that you could discover from this first generation of models. And so we then focused on kind of what's going on in the brain with those challenge images. So I'm going to sort of zoom in on those, take these images where primates are really good at. You know, we're not good at everything, but here's images we're very good at in this band here. And now we can look at the spread over models being either matched to us, sort of good at them. So we call those ANN 2.0 solved. In other words, they look just like us. And the ones where they look much worse than us here in red, no, not solved or challenge images. And we're going to compare kind of maybe what's different in the brain between these red and blue images. And can we get some insight as to maybe what should be changed on these models? I'm sorry, that should say ANN 2.0 performance. All of these are easy for primates. Again, as I already said, here's an example of the images of the ones that are solved and not solved. It's very hard to find specific things that you can map as to what makes an image hard or not. Trust us, we've tried and regressed all kinds of variables. I'm not going to tell you about that, but I'm showing you some images so you can see. But the question we wanted to ask is, first, can we ask, okay, these are challenging images. These ANNs are having problems with them. Can I really back up that statement I said earlier that IT and the ventral stream provides a good basis? Does it even solve these images itself? Maybe they're not even solved at IT and there's some magic downstream of the ventral stream. And so one of the first things we wanted to do is just like, let's record an IT cortex and see what's happening in those challenge images to kind of redo that loop I showed you earlier. So we put in some recording arrays, as I showed you earlier. We measure the spikes. We build the feature vectors that we usually do. We then build our linear decoders in the usual way that we've done before and ask how well do the solutions, how well can the neural populations explain these images? Do they solve them well or not when you just record directly out of IT cortex? And what we found was something interesting. So the big story is we found that they were solved, but they were not solved in exactly the way that we had kind of thought about it before. And let me give you a sense of that. So here's an IT population vector. This is a decode. And then now I'm going to show you that as a function of time. So if you look at now, I'm going to show you one of these solved images where both computer vision and brain networks get them right. And this image is the image of a face. And here's the decoder of saying it's successfully calling it a face. This is just, think of this as accuracy on the y-axis here. And this is a successful time of correctly saying this is a face. And we can quantify that here at around 100 milliseconds or so, really just after the IT neurons as a population start firing, what you're seeing here at the top, the activity level. Here's another image of a zebra. Okay, same kind of thing. Quite quickly, the IT population is readily able to say it's a zebra. Remember, these are images that computer vision systems that were compared to also solved quite easily. Now we go to some of these challenge images here. And what do we see in the brain? Well, here's an example of a car. We get this quite well, actually. We solve this, again, all of them are solved by us. Now the decode of IT, it shows something funny. There's a little bit of a lag and a longer time to reach the decode accuracy. Notice IT's firing throughout all of this here. Here's another image, is a foreshortened image of a dog. Same thing, a little bit of a lag and a longer time to solve. Notice the time scale here. We're talking about tens of milliseconds here, all in that 200 millisecond window I alluded to way at the beginning of my talk. But to highlight here, it's not as if you're waiting for the IT neurons of the system to start responding. The sort of initial wave of activities already occur, but sort of this later phase of IT response, it's somehow more linearly decodable to say this is the dog, whereas this early phase is not quite that way. That's how we interpret these results here. So again, this tells us something interesting is happening. You may already be thinking about, well, maybe there's something to do with recurrence and dynamics. And indeed, that was what was motivating a lot of this study. But we went ahead and quantified this for a whole bunch of images. Here's 20 images or so, and each is solved at a different time point, and we can quantify that as sort of measures to guide models. And we went ahead and quantified that for many. And the sort of big picture story here is that we found that for all ANN, all the ANN 2.0 not solved images, they were solved by the ventral visual stream output. They were linearly decodable in the IT population. And so that was already a finding. We didn't know that that was true. However, what we saw is that on average, the ventral stream required a bit more processing time, about 30 milliseconds to solve many of these so-called challenge images here. And I want to highlight for many of you here, remember I showed you behaving monkeys. These results exist even for passively viewing animals. In fact, it's very hard to see differences between active and passive animals. So the dynamics that are evoked and the mechanisms are sort of naturally evoked, even when just a fixating animal, we see these kind of dynamic effects and these solutions occurring. And this suggests that the brain utilizes what I'll refer to as automatically evoked recurrent computations, sort of subconscious, even for core recognition tasks that are just those first couple hundred of milliseconds. So some people have taken our prior work to say they think it's all feed forward. We never really thought it was all feed forward. We start with feed forward models as an approximation. And this is some of the first evidence, at least from our group, that we can say, look, there's some evidence that you're going to probably need some sort of recurrence here to fully explain these kind of data that are giving rise to the full power of the system that we measured more finely here. Okay, so a way to summarize that, and again, this is just kind of oversimplified, but give you kind of a big picture view, is we have these sort of early solved images in blue. It is kind of ANN solved images, and about 30 milliseconds later, you get these not solved images. Just reminding you that it's really a distribution in reality here. It's not a sort of two-part, not a two-chunk analysis, two-chunk processing stream. It's a continuum. But for ease of explaining, we'll just think of it as early and late. So early IT solutions and late phase IT solutions. And I think of this second phase as there's some sort of supercharge that's added somewhere in the brain that's appearing. We're measuring it in IT, but it may have to do with circuitry that lives outside of IT and maybe even outside of the ventral stream. And another interesting tidbit we noticed at the time is that the IT population match, that sort of early results from the Yeaman's work that I showed you earlier, the match of the models, like the feed-forward 2.0 models, was quite good in the early phase, but falls off pretty dramatically in the late phase here. So these ANN 2.0, these models don't align well. Their features don't align nearly as well at the late phase as they do in the early phase. And so another way to put that is shallow feed-forward ANN 2.0 models are a good approximation of the brain's first computed features, but they're not such a good approximation of these late phase computed features. Interestingly, the computer vision community started to build deeper and deeper models, and if you check their alignment, as models get deeper, they're actually starting to align better with these late phase solutions. So if you intuit all that, what you should now think of is that these deeper models, you can think of them as partially approximating the brain's late phase dynamic computations as something that they're approximating as a feed forward, just deeper nonlinear network that's more starting to align better with what the brain's doing in a more compact recurrent network. That's how we think about that overall, those overall set of results. So you might ask, okay, what's going on here? Just because, Jim, you're showing me these IT patterns coming out and they're dynamically changing and they're getting better over time, what needs to be added to the models to make them more brain-like and to sort of maybe make them better in this sense? So in other words, to put that as start with a neuroscience question is, where are these supercharged computations? Maybe they're in recurrence within the ventral stream. Maybe there's some downstream areas here. Maybe they're related to skip connections. There's all kinds of things they might be related to. And so we don't know the answer to this yet, but I'll show you a bit of work that we've done to get at it. So we asked, like, for instance, PFC cortex, is it involved here? And we focused a bit on this here. And in the interest of time, I'm just going to sort of tell you that sort of what we did was we went ahead and activated prefrontal cortex, and we compared the responses in activating PFC versus not inactivating PFC. And the idea is that if you inactivate PFC, you're going to remove its recurrent processing to the ventral stream. And what we found is that actually, and then go ahead and record an IT cortex and measure both the neural activity in IT and those population vectors, and also measure the animal's behavior. And we go ahead and take the images we used before, and we had the early solved and late solved. And just sort of big picture here in the interest of time, what we found was that, kind of consistent with this idea that ventral prefrontal cortex is adding some of the value in that late phase solution in IT, is that those early phase solution images were not at all affected by PFC silencing. But the late phase solution images, they were strongly affected in this later time points. Their change in their decode accuracy strongly affected by silencing PFC. That's at the neural level. And at the behavioral level, we saw stronger effects on the animal's behavioral deficits on the late phase than the early phase behavioral changes. All of this is consistent with the idea that PFC is adding some recurrent value. Interestingly, by silencing ventral PFC, we also made the IT cortex itself just more aligned with the feed-forward models in general. It's almost like we turned it into more of a feed-forward network, and we can measure that by model alignment measures that I'm not showing you here. Okay, So I just said this, the rapidly evoked PFC computations are one part of the recurrent pathways that seem to be involved in supercharging what we're seeing in the ventral stream here as one part of a large set of recurrent circuitry. You may now be asking, okay, that's cool, that's a good neuroscience paper, but what information is actually computed and transmitted back? Or I would say more concretely to the point I said earlier, what's the new model? How do we build the new ANN 3.0 models given these or other data that we and others have observed? And I don't know the answer to that question yet. What I do know is we've been starting to build recurrent models. Dan Yeaman's group has been building them. Others are building them too. And we don't have a great answer on this question yet. In fact, I view those experimental results as kind of material that newer models have to try to explain. We have to start to even include areas like PFC on these models, which are not included in these current models here. And Co is actually busy recording from PFC, probably as we speak, getting more constraint data on both the neural activity that can also be used to guide these model development. So this is sort of ongoing work to build even better models here based on those kind of recurrent ideas that have long been suspected, and now we can start to actually get traction on in this model space. I want to end my talk, if I have 5 minutes left, to talk about this piece here about evaluating the current best ANN models. So I kind of say that like, oh, it's easy, you just do that and then you go on and build a better model. This piece on the left turns out to be the challenging part of our field and the most difficult thing to do, and it deserves a lot of attention. It's not easy, and it's also not actually a rewarded activity. It's like being a referee at a soccer match to do this, right? And building models is more fun. That's sort of what the answers are going to be. But this is the hard part of the science that needs to be rewarded. And I'll sort of tell you what we've been doing on this. So remember, way back to my logical statement I said at the beginning, this part about best here is critical. And so best matching all the currently available data, how are we going to go ahead and do that and make that a reality rather than just say it on a slide here? How do we make it real? And remember, to make it real, I don't just mean, hey, we want the best model of IT and someone else has the best model of E4 and someone has the best model of it. I mean, we want, as a field, the best model of the whole ventral stream, and at some point, the whole model of the whole brain. We're starting with the ventral stream. We want a best model in all of these alignment points. So we need network alignment measures at multiple stages and multiple scales, single neuron level, voxel level. We might need to start making these cross species at some point. There's a lot to do when you start to get serious about comparing. But if we just stick a primate ventral stream, we thought we can make some traction on that. Let's try to set an example and do it and see how far we can get. And so when I say we, this is work led really, kudos to Martin Shrimp, who is a graduate student in my group. I've been working with a number of other groups on similar platforms. We developed an open source platform that we call the BrainScore platform. It's far bigger than my lab. Doesn't belong to my lab. It really belongs to the community. And it was really a kind of an attempt to live by this idea of let's actually build up a platform that can allow people to evaluate models on multiple neural metrics. So and have it be reproducible in that sense. So we have a platform where you have multiple metrics of different ventral stream stages shown here as columns, and on rows are different example models here. And if you go to the BrainScore site, you can click on these models and figure out where they came from or what these metrics are. And if you're interested in this general idea, Martin and I wrote a kind of piece with some others at Neuron, a Neuron Perspective about a year ago. And it tells you all the pros and cons and challenges of doing this and so forth. And if you're interested in the idea, I encourage you to read that. One key message I would give here is that data are not enough. You can't just put a bunch of data up somewhere and hope this is going to work. It's really data combined with metrics. For instance, weighted sums to match neurons, and a metric that I showed you earlier is one of many metrics. Those we call benchmarks, and you need many such benchmarks, and you need platforms that can help you execute those benchmarks reproducibly. Here's our current set of benchmarks on BrainScore. There's many of them. You see them growing. A lot of these are V1 benchmarks here. Again, the models are on the y-axis. Benchmarks are across the top here. I want to point out they're both neural and behavioral. Remember, that's what I mean by best brain alignment. We've also been starting to add engineering benchmarks, computer vision accuracy, other energetics benchmarks we're trying to put up here as well. And if you want to submit a model, if you are a modeler and you'd like to take advantage of this, you can submit a model and have it be evaluated on all these benchmarks, and your scores will be returned to you. And you can decide to post your model or not, publicly or not. We're not trying to shame anybody in terms of having a bad model. We're trying to provide help to see how well to give modelers guidance on if they're on the right track or not. So I want to give you sort of a sense of what this enables, and then I'll end my talk 2 slides after this. So examples of what BrainScore enables as a platform. So it incentivizes and tracks the building and dissemination of more accurate computable models, in this case of the ventral stream, but you can think of that more broadly in other areas and other areas as well, like language is an active area, and you heard again some of that from Jean-Remy. Here's an example of kind of what computer vision did is like they started to have optimization for ImageNet, and that led to great progress. We need to have optimization for things like brain score 1.0, and that will lead to better and better models of the mechanism that we and others are interested in whatever our subsystem is of interest. So that's just kind of incentivizing, motivating, and rewarding people who are building those models and giving them sort of a traction to do that. It also enables discovery. Remember, this is a multi-part problem. It's a systems level problem. So if you're working on V1, how would you ever know if your models of V1 have any relationship to improving overall system match? And by putting models together, by allowing people to put those components together, and we showed you an example of putting V1 with some other models, it allows you to see that. So here's an example of each dot is now a model. This is actually out of the BrainScore platform. Here's a V1 benchmark score, how well a model's V1 level matches. And here's its behavioral score at its output level on detailed patterns of core recognition behavior, sort of image by image patterns. And you see that better models for V1 tend to lead to better behavioral benchmark scores. And if we didn't have this kind of platform available as a field, we wouldn't be able to even know that what we're working on in V1 has any relationship with these kind of longer term behavioral goals. And this is already starting to happen now because we have these sort of end-to-end models, if you will. It also enables discovery of if and how brain alignment leads to improvements in other engineering uses. I mentioned some of this in computer vision a minute ago. This was actually the motivating, motivated the other direction for the initial ANN 2.0 models, that ImageNet performance that we and others were trying to optimize led to some of the best models on overall match to the brain. I showed you a version of this slide earlier, and you see this again happening in other fields, that just doing better on some of these things tends to lead to improvements on this. So the flow was from engineering and AI onto neuroscience. But then I showed you an example where the flow went the other way, neuroscience matching better V1. Now, again, each dot is a model, lead to better adversarial robustness, a slide I showed you earlier in the talk. And so by having these kind of engineering benchmarks in blue available, they allow you to kind of see where your neural ads are adding value or not on different engineering benchmarks. And most importantly, it makes our field guide against this, right? So if neuroscientists often ask, well, why don't you put in this or why don't you put in that? And Robert Yang said this in his talk. Well, we don't want to put in everything. We start putting feathers on the plane. We want to put in things that are related to the behavioral engineering goals that we're after, and that sort of allows us to focus efforts in a way that's going to be most productive. Guards against us building things that might look nice, but kind of not work or fail catastrophically. So this is, again, I've already mentioned this. This is a growing community of BrainScore. I encourage you, if you're interested in this, please reach out to us. We'd like help in shaping it. Please join us. There's lots of opportunity to help and get involved in various ways, whether it's modeling, data ad, benchmarking, and so forth. So this is my last slide here. I will just end with the take-home messages. So my first take-home message is scientific hypotheses are computable models. I don't think that should be controversial, but the computable models make reproducible predictions that do not require a human in the loop. The best hypotheses are those that are most predictably accurate. I don't think should be a controversial statement. But for brain science, accuracy means align with brain, which means you're going to need ANN models to make alignments with the brain, and a behavior, because you'd like to align at all levels if you could. And the claim is that the best neuroscientific hypotheses are computable ANN models that are most empirically aligned with the brain. This is a philosophical statement I said earlier that seems to somehow not yet be fully accepted by our field. The process is never finished. There's always a better model. I've said this a few times. In practice, however, the current best models, even though they're only not perfect, glass only half full, they're already demonstrably useful. I showed you neural control. I showed you some gains in computer vision. We have gains in other areas that I didn't have time to tell you about, but just having a better model in hand already gives you value. That being said, we're not done. As a scientist, we continue to experimentally identify gaps in the model to behavioral mismatches, model to brain mismatches. I showed you that with the recurrent neural network data, for example, there. And we see those gaps, and that can guide new ANN 3.0 model development. A key bottleneck for our field to do this is that you have to have shared ways to comprehensively evaluate these models. And we're doing our best, rather than just complaining that we don't have this. We're doing our best to try to help make that happen. I showed you the work by Martin Schrimpf and others to set up a BrainScore platform that is trying to do that. And I think others are doing that in their subfields as well. And I think that's a terrific move for the entire field. And please again, you're welcome to join in this, and I encourage you to reach out if you're interested. And with that, I'll say thank you and end my talk in an hour. Thank you.
Talk. And now I'll pass it over to Paul to take questions.
Yeah, that was great.
Really great.
Thanks, Jim. So because we're running late on time, and many of the questions that actually have been uploaded are the questions that you were anticipating, I'm sure, about interpretability, etc. And those are actually, I think, really good questions for the discussion in the panel in which you are. So I think I'm going to actually. There were questions by Ezekiel Williams, by Maxwell Matusel, a related question from John Krakauer. In the interest of time, I'm going to ask something that maybe a little different from Julien Voisin, who asked, let's imagine we have two artificial networks that fit human overperformance well. One presents a few biologically realistic features, the other doesn't. Do you think the former is more likely to help us understand our own brains? In addition, though, I'd like to add another comment made there by Vale Borghesani, who asked whether we should, I'll just say it quickly, shouldn't we also aim at models that break and fail in the same ways as humans does? In other words, having some properties such as, for example, exhibiting extinctions and negligence, etc., as a function of damage. In other words, that being part of your evaluation of the ANN model.
Yeah, I mean, those are both. I lost the first question, but I'll pick up on the second one because it's exactly right. Of course, I hope I was saying that multiple times. It's like you got to if someone says you're going to lesion the model and it should fail in the same way, that's exactly right? And I didn't get to talk about that, but that was part of the BMI work that I didn't show you, is that I don't view these models. The models now make predictions, and you can test them whether they're behavioral failure is an example. And yes, let's use the models as the hypothesis. Let's break them in a way that we think is analogous to the breaking in the experiment, and then let's see which ways they fail, and do they fail in exactly the same way as humans? And they're going to not fail perfectly in the same way as humans, and then we try to use that residual, so to speak, to update the models. And I think I gave you an example of that with our own work in recurrence. Again, I hope I'm not coming off as the ambassador of these are the final models, and anything the opposite. They are the current models, and they stand as hypotheses, and we use them in exactly that loop. And I think there's a trickier question, which may be related to the first one, just like there's so many brain measurements that we could start to check against. And how do we decide which ones to check against? And there's a lurking question there, which is really about the goals of the field in a way. I have personal answers to that, of how I think about that, but I maybe we can bring that up at the panel because I think it relates to the overall idea of what does it even mean to model or understand the brain. But I don't know if I channeled the first question well, Paul. Did I? Or maybe you want to repeat it if I didn't touch on it, because
well, it was just if you have two networks, if you have two networks, one which has more biologically realistic features than another, do you then believe that the one with the more biologically realistic features is more likely to help us understand the brain?
Well, it's sort of that I operationalize that as sort of what do we put on the brain score platform, right? So if we had a score for biological realism, then by that score it would be the highest. But I mean, that's why I meant by it, it's hard to sort of say what is best. So that's kind of I read that as an anatomy question. But if it was a functional question like, hey, this feature leads to a V1 slightly better, then that should, that would show up as a better model on the overall match to the brain. Now, interestingly, what if we get a better V1 match and a worse behavioral match? That's what I mean by we're forced to choose. So far, these things tend to track together. At some point, they will deviate, and we have to decide, are we modeling V1 at all its detail, or remodeling the behavior output, and sort of forces neuroscience not be one field, but a sort of conglomerate of fields. And I think that's maybe the interesting panel discussion. It's like, why do we want to model V1 in every detail if it doesn't relate to behavior, right? So there's those kind of lurking questions that I think that question relates to. But I agree with the spirit of, check the alignment. It's just the details matter. What do we mean by how are we going to measure that? So.
Indeed. So I would again invite some of the people whose questions I wasn't able to ask to repost them again when we have the panel discussion, because I think they're completely relevant, and we'd all like to hear what Jim has to say, as well as the other panelists. But anyway, so in the interest of getting to that, then we'll just thank you again, Jim, for a wonderful talk.
Wonderful talk. Thank you so much.
And please join us now in the panel, reverse